Okay, hypothesis testing. Handout 8 is our one sample test. Handout 9 is two sample test. Now, Handout 9 is just an extension from Handout 8. So once you know the one sample test, two sample test is just you keep on writing something longer. That's all. The ideas are the same. What are we testing? For now, we are only testing the population mean, nothing else. We don't touch population variance, we don't touch the population distribution, nothing else. For one sample test, we focus on one variable. This variable X. Suppose that we know it's normal, then it comes with two parameters, population mean, population variance. Okay, just keep in mind whenever you hear population, that means it's the distribution of the variable. When you hear sample, okay, sample means sample variance are not these two. They refer to whatever you get in your real life from the sample you have. We want to test mu. Now, maybe you have the hypothesis from somewhere, from authority, or you want to test whether this mu equals a value, right? This value we show as mu naught. Okay, this is just a number. We don't think too much. All the notations are important. No, this mu is the population mean. This is a value, a number that you want to test. This is H naught, the null hypothesis. Now for H1, three options. For this course, we have a very straightforward way to choose which pair of hypotheses we are working on. But in real life, even what to put in H naught, what to put in H1 is something serious. It's a serious topic in real life. But for this course, we are always giving you in questions H naught, H1. Okay, don't worry about where to write what. If you see the first two pairs, they are one-sided test because you test either this equal or greater or less. So one side. The third pair is called two-sided test. Keep in mind that H naught, H1 are always complementary. So whenever you see this H1 as mu greater, then the hidden message, okay, it's a hidden message, that H naught is in fact not only equal, but also less than or equal to, because they have to give you the complete set of all options for mu. So they have to be complementary. Then why do we always show this equal in H naught? Because we want to make your life simple, right? As simple as that. In our solutions, we always need you to substitute mu by a fixed value, right? We don't want you, because it's less than, so I can choose any value less than that number. No, you don't have that flexibility. So we just want to make it crystal clear that you substitute mu in your calculations using this value. Now you may wonder, what calculation? I'll show you in 10 minutes. Okay, just wait. Right, this is the introduction to hypotheses. Again, whatever you put in your null hypothesis, in your alternative hypothesis, it's not something you have to believe. What you need to believe is your sample. Okay, the sample is the fact that you should not argue with. To do the hypothesis test, we need the evidence. The evidence is from the random sample. The random sample is collected from the distribution of X, for example, X is the height of a student, then you get a random sample, so just some random independent students to measure their heights. So this random sample, first student's height, second student's height, we have a group of them. The random sample is the only thing you should trust in any hypothesis tests. From the random sample, obviously we know the sample size N, sample mean, right? Notice the language I'm using, sample, okay? Sample mean and sample standard deviation. Since we are testing mu, population mean, the sample mean is an unbiased estimator for population mean. So if this group of students have a height of this value, then you learn from confidence interval that the population mean should not be too far away from this sample mean. So this shows how important the random sample is, because the random sample is something we trust. We use the sample to reject or not reject H naught, right? This is the whole idea of hypothesis testing. Now let's start with maybe I do a brief reminder of the last questions, uh, the last question you saw in the previous lecture. Then I'll remind you of alpha, everything else. In the last example, the variable x is the fat content in the lunchbox. Suppose that x is normal. We don't know population mean for sure because we are testing mu, but sigma is given. So now we don't do any fancy number, so sigma is 1. The test is on whether mu is 5, so 5 grams of fat in the lunchbox. Alternatively, mu is more than 5. So if the fat content in general in the lunchbox is too much, then the customer would complain. A random sample. Suppose that a customer collected 10 lunchboxes. It turns out that these 10 lunchboxes have the average fat content of 5.6 grams. Can you say that because 5.6 is more than 5, so I support H1, I reject H0, right? Just because 5.6 is greater than 5, so it supports that, so we reject the null hypothesis. You cannot. You can't make the claim because this is sample mean, right? This is not mu. So sample mean does not have to be exactly your population mean. So you can't make the direct connection and then it's greater than 5, etc. 5.6 is greater than 5, but is it significantly greater than 5? Right? It is the significance that you have to show. How much greater than 5 is significantly greater? Let's first use the critical region method. Okay, I write a small list of bullet points here. For both Handout 8 and Handout 9, we have 3 methods. In any hypothesis testing, there are 3 methods. The first one is called critical region method. The second one is p-value. Today, I want to cover these two. The third one is confidence interval. We had already a separate handout on confidence interval, so I hope you still have some memory on it, so we don't spend too much time. But these two things are new, so we need to talk more about them. So these are the three methods. Once you understand them in Handout 8, Handout 9 has exact three, right? We don't have the number 4 method. Now, what is critical region? In the first part, a critical region is suggested for you, right? It's a proposal. The critical region is given as x bar is more than 5.5. Now first, whenever you see a critical region, now of course in real life or in your final exam, nobody will give you a critical region and ask you, is it good? You have to give a critical region by yourself. Critical region is a region. Okay, this is a definition. It's not that tight, but you need to understand the idea. The critical region is a region that if your sample is too bad in supporting H naught, then you reject H naught. Right? Very straightforward. So the critical region is definitely interval. Right? It's an interval such that your random sample, how do you judge if a random sample is too bad in supporting H naught? You look at N, definitely not. You look at the sample mean. So if the sample mean is not supporting H naught, then you reject H naught, right? As simple as that. That's why the critical region, okay, let me use a red pen. The critical region is for your sample mean, right? You never see mu there. If your sample mean is too bad in supporting H naught, which side is too bad? Why it is greater, right? It's not less. Because if the sample mean is too large, now for example, in my 10 lunch boxes, their average fat content is 10 grams or 20 grams. If it's so large, I would say because the sample mean is so large, most likely the population mean is very large as well. If it's so large, it can't be 5. It has to be greater than 5. So it is the larger than, right? This larger than that would reject H naught and support H1. That explains why it's larger. Then this value, 5.5, it's given to you, okay, because it's just a start. Why it's 5.5? Can it be 5? It can never be 5. You cannot choose exact the same value as the hypothesized in your null hypothesis to be the critical value you choose in your critical region. Because we always need to give a margin, right? You can't be so uptight. So if your sample mean is greater than 5, then I support this, I reject that. No, you have to give a safety margin. So that explains why it cannot be 5. So it has to be greater than 5. Then why can't it be less than 5? Suppose that this is 4.5. If your sample mean is greater than 4.5, is it sufficient to reject H naught, accept H1? You cannot, right? If your sample mean is more than 4.5, then maybe mu is exactly 5 because 5 is greater than 4.5. So I use different ways to discuss these three parts. Every part you need to ask yourself, okay, this is where the concepts come in. Why is X bar not mu? Why is greater, not less? Now you can use equal as well, greater than or equal to, it doesn't matter. Why is 5.5, not 4.5, not 5? Okay, there are so many questions. Since I'm doing the recording, if you missed any parts, you can just watch this small section again. With this proposed critical region, I've argued that these three parts seem to make sense, but then we have to justify whether this 5.5 is well chosen. Right? Why can't it be 5.6? Why it's not 5.1? What makes it a reasonable proposed critical region? So how to show 5.5 is workable? You judge by the value of alpha. Now, what is alpha? Alpha, the name of this alpha was already given in the confidence interval handout. It's called the significance level. In confidence interval handout, we use 1 minus alpha as the confidence level. Now in here, alpha is still called significance level, but the definition of it is more precise. It's the probability of making type 1 error in your hypothesis test. So alpha is a probability. So it can't be greater than 1, can't be negative. Too many students write in the wrong way by ignoring this big P here. Alpha is not type 1 error, it's the probability of making type 1 error. Let's keep writing. What is type 1 error? When you make a decision to conclude your hypothesis test, sometimes you make the wrong decision because sometimes your sample is misleading you. Right? If your evidence is, for example, skewed, then very likely you make the wrong decision. There are two possible ways to make wrong decisions. One is called type 1 error, the other is the type 2 error. I believe these two definitions were introduced in the first day of Handout 8. So there's a little table you really need to make sure of that you fully understand, because the two types of errors are very easy to be confused. The way of not being confused is you train your muscle memory. You have to keep writing. Right? After you write maybe 5 times, then at least the type 1 error will be inbuilt in your, at least the muscles in the fingers. Type 1 error is you reject H naught when H naught is true. So if something is true and you reject it, you are making a mistake. That mistake is the type 1 error. Reject H naught based on what? So what would make you to reject H naught? The critical region, right? We are using the critical region method right now. So if your sample mean is too large, then you reject H naught, right? So we reject H naught when this happens. So if the sample is not supporting H naught, then we reject H naught. So I copy exactly the critical region to match this underlined part. When it is true, what is true? H naught is true. Or I just write when H naught is true. When H naught is true, mu is 5. So now I showed some math. You can't solve a question by writing English always. So we have some math now. Now we come to this. Don't forget, we need a probability. So inside the probability, we need a variable. We need a distribution of the variable. The variable here is x bar. So it's the probability that your sample mean is greater than 5.5 when this condition is true. Since x bar is the variable, a short reminder, what is x bar? Okay, we start with x as the variable. So x is normal. What is x bar? This is handout 4, your favorite part, linear function of random variables. It's you add the first lunchbox content, the fat in the first lunchbox, the fat in the second, and the 10th. You add them up, divide by the total number of lunchboxes. That gives you x bar. This is what? A linear function of normal variables. So x bar is normal. The mean of x bar, the variance of x bar. So x bar has that normal distribution with this and that. We don't know mu, but we are given sigma, and we know n. Right? N is the 10 large boxes. Now it's the time to standardize x bar to z. Okay, I show you. Standardization. X bar minus mu do the same to the 5.5. Don't forget the condition because we have not used mu equals 5. So I show this step just to get the z. Now I have a good z statistic on this side. On the other side, this is the moment. Okay, this is a very safe moment to substitute. 5.5 minus mu 5. Sigma is 1. And now I don't want to show you how to use the z table. We have these calculated as 1, because this is 1.58. Use your z table that gives you this value. Okay, this is alpha. We started with here, and then so many things going on. Probably once you get to the end, you don't know what you are doing. Okay, this is the moment to bring you back to alpha. So this 0.05 something is the probability to make type 1 error. Because it's a probability to make an error, you don't want it to be large, right? Nobody enjoys making errors all the time. Is this value small enough for you? In confidence interval handout, I said that the significance level by default is 0.05. Right? According to the topic, according to whatever research you are doing, you can choose even smaller or slightly larger alpha. But is this good enough? Maybe it is. I don't know. This value is reasonable. Right? It's not 0.6, that would be really unreasonable. So it's 0.0 around 6. Right? It's reasonably small. If this is small enough for you for this research, then you just say this critical region is well chosen. So everything works together. But if this value is not so good, for example, if we really want to use alpha as 0.05. So we don't want to see this as 0.6, we want to see 0.05 to be the alpha. What to do to make alpha to be a little bit smaller, right? Does it make sense? Oh, I changed this 5. I changed my idea. No, you need to change your critical region. So you find a critical region to give you alpha value of this constant. So see how we got the alpha. When we calculated this alpha, we use the critical region. So if this is not 5.5, it's another value, then we can get whatever alpha value you want in the end. This approach is what is used in your real hypothesis testing. As I said, nobody would give you, oh, let's try one. How many do we want to try? Right? This is not any realistic approach. You can't work with a critical region first and then find the corresponding alpha. When you do any hypothesis test, alpha value should be determined in the very beginning. You don't change your idea. Otherwise, it's unethical. It's cheating. So you fix your idea of alpha based on whatever field you're working on. Now we have 0.05. Then starting with 0.05 as the chosen alpha. How to find this critical region? Okay, now we are getting serious. This is the very first method in hypothesis testing. I show all the work. It would look very similar to above, but since we don't know 5.5, okay, let's see how to find it in exact same steps. Alpha. Definition. Okay, don't try to cut corners in your final exam. You have so much time to write the work. Definition for alpha. Next thing, definition of type 1 error. Now we come to the reject H naught. If what happens, if your sample is not supporting H naught, then you reject H naught. I always keep this common sense in your head. Right? The hypothesis test is really not a mystery. These are all common sense. That's why people accept these methods, because it should make sense to everyone. Now, if your sample mean is too bad in supporting the proposed value, so the sample mean is too bad. I argued back and forth on the look of the critical region. So if your sample mean is too large, then what value? We can't use 5.5 now. We use just any sign. You can use ABC, you can use whatever sign. I use a start value. So this is the constant to be found in the end of the work. But what you need to make sure, you show X bar, not X, not mu. It has to be greater. Now you can use greater than or equal to, it's also allowed, but not less, or not equal. So these two parts coming from you. Okay, everything is coming from you, but this one You can use whatever symbol you like. Right? This is the critical region when it is true, when H0 is true. That comes from the mu equals 5. From here, since we have two things, I hope you are clear that x bar is the variable. This is the constant. So of course, the same logic, we standardize x bar to be the z. Then you substitute whatever values available. Z is greater than something. We don't know what the value is, but we know that this probability started with alpha. Alpha value is given. So we have a probability that Z is greater than a value with a 0.05. This is the bell curve for Z. All the Z values are at the bottom. The line of symmetry is exactly the vertical axis. So the curve is the PDF of the Z distribution. The probability is Z greater than a positive value or a negative value to give you a probability of this small. It has to be a positive value so that greater, it means the Z values are these, right? Then above these Z values, you have an area of this little, right? This is how you match the probability with the sketch. How to find this Z percentile? You can feel free to use the Z table, right, in the correct way, of course. Then you get 1.64 or 1.65. Or you can use the last row of T table. Now, if you wonder, why? What are you talking about? That means you did not watch my video on the second day of confidence interval, where I introduced the T table. So this is the last row of T table. It's very handy. It's much faster to use this one, the last row of T table. Okay, this value, 1.645, is this unknown, is this expression. So I connect the two. Solve for this unknown constant. It turns out to be this. Then what is this x star? It's in our critical region. So I make a statement that finally I know the critical region that gives alpha at 0.05. So the critical region is, make this expression complete. X bar greater than this 5.52. So if your sample mean, what is sample mean? The average fat content in your 10 large boxes. If the sample mean is greater than 5.52, that means they claimed 5 grams is too little. the population mean of the fat content should be greater than 5 because my sample gives a very large. Oh, okay, this is not our sample. Let's look at our sample, right? Our random sample gives, I show this observed, that means from the sample we have. This is given from the question, right? 10 lunch boxes give you 5.6 as their average fat content. Our lunch boxes, 5.6. 5.6 is greater than that, meaning our sample mean falls inside the critical region. If it falls inside the critical region, then we reject H naught at 0.05 significance level. Okay, this is the first time I show you how to do the critical region method. This is the complete work of the first method. You really need to follow the same work, right? Every line is 1 point, is as valuable as that. So you don't judge everything in your head, you write things down. In the conclusion part, I mentioned again, we are using 0.05 significance level because in part C, which I'm not going to show in all the detail, if we change our alpha, so for example, if the customer is a patient with some health issue, and the patient really don't want high fat content in lunch boxes, then they make this alpha to be smaller. If alpha has a different value, do you think we use the same critical region? Definitely not. Because from the previous two parts, I hope you've seen how the critical region is closely related to your alpha. So now the alpha is different, the critical region, you have seen the complete work of finding this critical region in the last lecture, so I'm not going to show that. Critical region practice of the work. Critical region is found to be X bar is greater than 5.74. 5.74, okay, I use this critical region to conclude the test. Our sample has the average of 5.6. 5.6 is not greater than 5.74. 5.6, our sample mean, does not fall inside the critical region. So where does it fall? It falls into the acceptance region. Critical region and acceptance region are complementary. Right? They give you the full set of all real values. So because our sample mean does not fall in the critical region, conclusion, we fail to reject H naught at 0.01 significance level. I have the two parts very close to each other just to compare. We've got the opposite conclusions, right? The first one is we reject H naught. The second one, we do not reject H naught. What has caused this conflict? Is it our random sample? No, we are using the same 10 large boxes. The only reason is we've chosen different alpha. So this shows again how important alpha is. As I said some time ago today, that alpha should be chosen before you do the hypothesis testing, even before you go out to get a random sample. Otherwise, it's really cheating, because if you want to cheat, once you have your random sample, you say, oh, I need to choose the alpha according to what I want. But that is unethical. So I showed you all about critical region. Now we move to p-value as the second method. What is p-value? P-value is a probability. So now we move to a different method. Let's forget completely of the critical region for the time being. And I will connect the two methods once you know more about p-value. Now, p-value is a probability that your sample mean is this sample mean. I show this capital X bar as a variable. It's not your current sample mean. Right? I use observed as the current sample mean. The sample mean is any sample mean is worse than your current sample mean in supporting H naught, if H naught is true. This definition is not very tight and it's quite confusing, but I think it makes a lot of sense. Let's try with our lunchbox example. So the lunchbox fat content in one box is X. All the statements before. And then the sample of 10 lunch boxes with average fat 5.6 grams. With all these, let's try to write out the p-value. So we have X bar observed, right? That's the easier part. The big decision is what is worse than the current sample mean in supporting H naught, right? This phrase is the confusing one. If H naught is true, we know very clearly when H naught is true, it means mu is 5, that's all. We can leave that. So which side of X bar compared to this 5.6 is worse in supporting H naught? If it's worse in supporting H naught, it means it's better in supporting H1, right? Because they are complementary. The sample mean compared to this 5.6. So the key was in supporting H naught is which side do you choose? Do you choose greater or less? Right? It can't be equal because this is a normal variable. If it's equal, the probability is 0 because any continuous variable to be equal to a value is 0 probability. So choose your side. Now let's think. The sample mean currently is 5.6. If X bar is more, previously I argued with if your 10 lunch boxes have the average fat content as let's take an extreme 20 grams. If you have 20 grams of fat in your 10 lunch boxes on average, you have to support each one because it's ridiculously large. That shows the greater your average fat content is, the more you support each one, the worse is supporting each one. So this is really the critical decision. Now you can imagine if I flip the sign of the H1, so if it's less, then it's less. So when you have a peaceful moment, when you are alone, think this through very carefully. Because we have X bar, right? You can't do much wrong if you know the definition, and we have this value given. So this little bit is the phrase that X bar is worse than X bar observed in supporting H naught condition. If H naught is true, mu is 5. But this is the easier part. Once you are able to write this out, you may think, oh, it looks very similar to the previous method. Again, I don't want to pull back that critical region method to confuse you right now. Let's just move ahead. X bar is the variable, which is normal, right? The same argument as before, but now I need to show the Z. Standardization of X bar. (5.6 minus mu, substitute. Also, sigma n. So I have a Z greater than 1.9. Use the Z table. You can't use the last rule of T table here for sure. You get 0.0287. This is the p-value. 0.0 around 3, right? 0.03 is the probability to have a worse sample than the sample we have in supporting H naught when H naught is true. Then what to do with this p-value? Let's think in two extreme cases. What if this p-value is extremely small? For example, we have this p-value almost 0. What does it mean? If p-value is almost 0, that means it's impossible to have a sample mean that is worse than the sample mean you've got in supporting H naught, when H naught is true. If it's impossible to have a worse sample than the one you've got, it means the sample right now is already very bad, right? It's impossible to find a worse one. If the current sample is so bad already in supporting H naught, then what should you do? You don't support H naught. I repeat, if it's impossible to find a worse one than the one you have in supporting H naught, that means the current one, the current sample, is already very bad in supporting H naught. Then you make the decision that I don't support H naught. So if your p-value is very small, you reject H naught. On the other hand, if your p-value is very large, for example, if your p-value is almost 1, that means it's so easy to find a worse sample than the one you have in supporting H naught. If it's so easy to find a worse one, it means the current one is very good, right? It's so good in supporting H naught. If it's so good, then we do support H naught. Now, how to decide if the p-value is too small in supporting H naught? We judge by the comparison of p-value with alpha. So this is not that, oh, we don't know what to do now, then we randomly pull out alpha to rescue. No, it's a theorem that people have proven. If p-value is less than alpha, alpha is a very small value, right? By default, it's 0.05, sometimes 0.01 or even smaller. So if p-value is even smaller than this little value, then p-value is too small. As I've argued, when p-value is too small, we don't support H naught. Right? This theorem is probably the shortest theorem you've ever seen, but it's very powerful. Now we know what to do with our calculated p-value. P-value should be compared with alpha. Now, in the previous examples on the same launch boxes, we have alpha 0.05 or 0.01. So if you choose different alpha values, when we had the critical region method, we got exactly opposite conclusions. Let's see for now. So if alpha is 0.05, our p-value is 0.0287. It is less than alpha. According to the theorem, p-value less than alpha, then we reject H naught at 0.05 significance level. If alpha is 0.01, does p-value change? No. P-value was calculated without the use of alpha. So p-value will not change according to your alpha. So we compare the same p-value with alpha. This time, it's greater than alpha, right? Because alpha is 0.01. Conclusion, we do not reject H naught. As I said, always mention the significance level you are using. With different alpha values, we got the same conclusions as in the critical region methods. Again, they are completely the opposite conclusions. That shows again your alpha is really important. Let's do an example where we'll see the two methods together. And next time, I have the confidence that next time I'll see you in person. So next time we'll do again the two methods. So from today until the final exam, you will see critical region, p-value, every day. Right? Whenever you see me, you see the two methods. And also from next time, you will see the confidence interval. X here is the polling level measured in a car. There's a company producing the pollen filter for the cars. And the claim is with their filters, it can keep the pollen level below 5. That's why I introduced X as the pollen level measured in the car, of course, fitted with that filter. The question tells you that the X variable is normal. Sigma is also given. According to the manufacturer's claim, we are doing mu. So if the company claims that my filter can keep the pollen level below 5, does it mean that they are making the claim on X? X is less than 5? Never. Nobody would claim that X is less than 5 because X is the pollen level randomly measured in one car, right? If something, right, in a very bad season when the pollens are so high outside the car, then probably once in your lifetime, X is measured as greater than 5. Nobody can guarantee that every time you measure, the value is less than 5. So the safest way, the practical way, is to claim that mu is less than 5. So on average, in general, the average level, which is mu, is less than 5. Now mu is less than 5 is put in H1 because we do need this little equal for our calculations. Right? In the previous calculations, you saw me using this mu equals a fixed value, right, all the time. So we do need this little equal. Then let's make our alpha as a fixed constant. Now we need the evidence. We have 20 cars fitted with this pollen filter. They are randomly measured at different times, and their average pollen level is 4.8. Let's do this misleading question again. 4.8 is less than 5. So we support H1, we reject H0. Is it right? Of course not. Why? We need to do hypothesis testing to see if 4.8 is significantly less than 5. Right? You can't say, oh, because it's less, so I'm good with this. No, you need to prove. Let's do the critical region method first. Critical region is a method that if your sample mean does not support H0, then you reject H0. What kind of sample mean would not support mu is 5? Again, if it does not support mu equals 5, it would support mu is less than 5. So complementary. If the sample mean, now if you are confused, you can always just throw some random numbers to make sense. X bar the sample mean, if the sample mean is 1, right? If your sample mean is 1, you would think that the population mean should be around 1 as well, right? So the population mean should be less than 5. 5 is an overestimate. You will not support that, you support this. On the other hand, if your sample mean is 100, now it can't be 100. Okay, for example, it's 10. If your population mean is around 10, it can't be less than 5, so you would support this. So it is the smaller the sample mean, the less you support H0, the more you support H1. So maybe I've been talking too fast, but again, you make sense of this one and that. This star value is a number that you will find through the work. Okay, let's do it. Critical region method starts with alpha. Do the same definition of alpha, definition of type 1 error. Reject H0. What makes you to reject H0? When the sample is too bad in supporting H0, then you reject H0. So if the X bar is too small, when H0 is. I wrote false. Can't believe it. When it is true, right? You reject something that's true, you're making a mistake. If you reject something which is false, that, by the way, that probability is defined as the power of the test. When H0 is true, that standardization X star is the unknown constant, substitute everything else. Alpha, no, sigma, 1.5. Now you can't do much because you are having this expression with the unknown constant. This is the moment to look back where you started with. It is alpha. Do we know alpha? 0.05. Do you get a point by drawing this bell curve? No, you don't. But this is very helpful in avoiding mistakes. We have a probability that z is less than something. That means we are looking to the left of this value. So z values are all here, to the left of a certain z value to have an area of only 5%. To the left of something, I need a small area. This is the only option. So this unknown value has to be negative to give you a small probability to its left. I tell you a statistic, 80% of students in the final exam would make the wrong choice. It will give me something there and they connect, oh, all good. That's very bad. How to find this negative z value? You have to start with a positive z and then match to the negative side. In the previous example, we had the 0.05 to the positive side, right? 1.645 to the right of it. Why this time is to the right? Because we have z greater, right? I'm drawing this to show the probability. Because with numbers, sometimes you are not so clear what the numbers mean. But once you give an area, the total area is 1, so this little bit, this tail is 5%. So I match to the negative side. And this is our unknown, this expression. Connect the two find this value, make a statement to show that you found the critical region. So the critical region is sample mean is less than 4.45. Let's pause here for a second. Does this critical region make sense? Now first, it's X bar, right? That makes sense. Critical region is for sample mean. So if your random sample has an average polling level that's less than 4.45, then the population mean should be less than 5, right? It can't be more than 5 because your sample has polling level even less than this. If it's even less than this, mu should be less than 5. Now use this critical region to draw conclusion. By drawing conclusion, that means you need to reject H naught or you do not reject H naught. So let's see what our sample has as a sample mean. It is 4.8. 4.8 is not that small, right? So which does not fall. You can use it's greater than 4.45 or you can write a sentence which does not fall in the critical region. So we cannot reject H naught. In part B, we are not getting to p-value yet. I want to remind you of beta. We've never talked about beta today. What is beta? By definition, it's the probability of making type 2 error. What is type 2 error? You accept H naught when it's false. I'm not so restrict on this word accept because many people don't accept. They would say fail to reject H naught. But for me, let's not be so strict. Of course, to be precise, you should say fail to reject H naught, but it's fine. What happens to make you to accept H naught? What happens for you to reject H naught? To reject H naught, we write the critical region. So now, to accept H naught, we write the opposite of critical region, right? You write the acceptance region. Critical region is this. So acceptance region is the complement. You can use greater or greater than or equal to. When it is false. So when H naught is false, so mu, when H naught is false, H1 is true. If H1 is true, what is the mu value? The question has given you the mu value as 4. Okay, it's not that it's up to you. We make things so easy for you. You just need to look around to find this 4 in the question. The question tells you for part B. So we have the probability again for X bar. You standardize X bar. So we have a beta value now. Beta is a probability to make another type of error. We don't want to make any types of errors. So we want beta value to be small as well. This result, 0.09, oh, this is so large. Oh, believe me, it's not that bad. Our requirement is to make alpha as small as the required alpha in that research field. Right? This was like a must. But with beta, people are more relaxed because, to start with, some people may argue, who tells you it must be 4, right? Can't it be 4.1? Because nobody knows mu. Now, if you know mu, what's the whole point of testing mu? So this is just a proposed value. If you change this 4 into another value, I'm sure you can see the calculation. So dependent on this 4, then beta value will change. So this beta value is not as strict as alpha, but you don't want to make type 2 error too easily. Okay, now we have this beta value. Do we use this value to conclude the test? We don't. Beta is not one of our methods in hypothesis testing. So you find the beta value in the end to give you that's part of the sample size estimation technique. As I said in the beginning of this class, that in the end of the semester, we have 2 days of free time where I really want to show you how to use this beta because we've been ignoring beta for 2 days, which is not nice. So we'll use beta to work with alpha to decide what's the best sample size. Right? You can't just go out and collect as many or as few as you want. There must be a guidance of the sample size n. We leave this question for now. Next time, I'll continue to part C, where we calculate the p-value. So today, we did not move on. I did not cover what is required on the handout, but I really believe that a solid foundation on this critical region and the p-value is really, it will be very helpful. So after today's lecture, please go through the definitions. There are so many new definitions in hypothesis testing. Please write them down on a very, use your best handwriting on a clean sheet of paper just to write down all the definitions, starting with this, right? And for example, the definition of alpha, the definition of type 1 error, and today we have a very important new concept, p-value. There will be more coming. So just keep that clean sheet of paper with you because you will need to use it to review and also to move to handout 9. Okay, that's all I have for today. If you have questions, you can stay on a little bit and ask me. If not, you just move to the next class.